It's a great pleasure to be here and fun to be among physicists. I mean, I work among physicists because in the Met Service, actually in the Met Service, we get a little bit picky about names here, but the Met Office, just like the Football League and the Football Association, is the British Met Office. So we're the Met Service. Met Eireann, of course. We brand ourselves just to distinguish ourselves from all those other Met people. But the Met very unpredictable. The Met Service is almost entirely peopled by physicists and mathematicians, so you can imagine what a fun place that is. But I see I'm probably the only person with a tie here, so I probably sold out or something over the years. It was interesting listening to, reminding myself, I suppose, of being reminded of both the astrophysics and the quantum physics, both of which were areas where in my earlier career, undergraduate career and so on, I took an interest. And realizing that a lot of that stuff is still very relevant to what I do now, the meteorology. A lot of the uncertainty, a lot of the odd things that happen there are translatable. The difference, of course, with meteorology is that it's something that we all feel and work with and go outside and get wet or warm or cold or whatever. So it has a very, very immediate impact on what we all do and how we all live and so on. So it's a very practical science. In that sense, we're very conscious, those of us who work in the media to some extent, and I don't do it to the extent that I used to, that we are to some extent a kind of the front page of science. For a lot of people, we're probably the only scientists that they see or listen to on a regular basis or a routine basis. So that gives us a fair bit of responsibility to try and represent this endeavour, this scientific endeavour to some extent to the outside world, to those who are as yet have not seen the light, so to speak. So I'm going to talk a bit about flooding because, it's topical, we've seen plenty about it. And in some ways what I want to talk to you about is to explain a little bit about flooding. And also, I think it harks back to something that Shane said in his talk about there's always going to be a need for people researching at the edges of science and pushing forward the boundaries. There's also a huge need for there to be a good understanding of science and scientific and technical topics among the general population so that we can make educated decisions and informed decisions. And this is something we're really missing in this country because many technical and scientific things are seen as, well, we'll leave that to the people over there to worry about, fellows with pointy heads or whatever, and we'll just get on with whatever. We don't have the knowledge maybe, the application, the interest to think through things, or the ability, or we haven't been taught to think through the ability to think through things in a rigorous fashion and have a rigorous line of argument, such as is normal to us as scientists, but a lot of people don't work like that. And that is a problem when we come to the real issues, many of which are out there on your election posters, to do with power grids or with nuclear, or with, in this case, flooding. And what is flooding? I suppose, simply put, flooding is water where you don't want it to be. So the water has to come, and it has to be somewhere where you don't want it. And if you think about it, the second part of it is actually as important as the first. And creating a place where you don't want water is, of course, part of the problem, because we've done lots of that in the last 20, 30, 40, 50 years. We've created lots of places where really it would be better if water wasn't, but water does come there. So that's been one of the issues about understanding technically what flooding is. So we recognise effectively three different kinds of flooding, which are, coming back to our Latin, fluvial, and if you want to stick with Latin, littoral, or coastal. So there's three different kinds of flooding, and they've all got different reasons why each of them happens. So flooding is not simple. I mean, it's a simple problem if you're standing in your kitchen and there's 30 centimetres of water. You're trying to lift everything up. I mean, it's simple in that sense. There's too much water in your kitchen. But why there happen to be too much water in your kitchen is a rather complex issue. It can be a rather complex issue. So we'll start with the fluvial, which is effectively river flooding, like Annalivia, fluvius, and so on, rivers. And that's probably seen it in the media a lot in the last couple of days. There's been lots of it through the Balkans, and earlier in the week it was up over other parts of Eastern Europe, the Czech Republic and Slovakia, down through Hungary and Austria, places like that. So fluvial is rivers. What are rivers? Rivers are places which gather together the water that falls within a catchment area. Catchment is effectively an area bounded by high ground in some respects. So everything that falls within this area, like this saucer, kind of ends up, as water tends to, given gravity, down at the bottom of it and into some river bed. So a river is a collection of water that's come from a large area. And of course, the longer the river and so on, the larger the area. Also, the shape of the area that it's come from is going to be critical here. Because some rivers are very steep. So they very quickly collect the water and deposit it down along through the riverbed and out into the lake or the river or wherever, the sea I should say, or wherever it discharges. Others are very slow because they're very flat. That seems fairly obvious, but next time you hear somebody wondering about draining the Shannon, and dredging the Shannon, and anything else to do with the Shannon, ask them, do they know the fall in the Shannon from Loch Allen, the top end, to Loch Derg at the bottom? So what is the height difference between those 2 points? And the answer is that it's about the height of a 2-story house. So you can imagine, the flow with that sort of slope, which is not zero, obviously, but very close to it. Pretty close to it. So the Shannon is not really a river. Shannon's a big lake. There is one way to drain the Shannon, in my view, is to start around about Athlone and to dig a big trench across into Galway and empty it out that way. But I think that might upset a few people. Not least the people you're digging the trench for. And the people down below who won't get any water anymore. On the other hand, you've got a river like the Dodder, which is a very quick river, so anything that falls into the Dublin Mountains is going to be in Dublin Bay within probably 12 to 18 hours. Whereas stuff that falls in Leitrim, into the Shannon catchment, takes a month to get to the far end. A month. And you can't really do much about that. You can't make it go faster because it's just flowing under gravity. So there's 2 different, this is all within river flooding, there's 2 entirely different problems. So if you think of, some of you might remember in Cornwall, they had big flooding also in Cumbria. They had big flooding there in Britain back in the late noughties, as we should call them, I suppose, 2007, 2008, 2009. And they were instances of very, very fast-flowing rivers, where there was a lot of water fell into the catchment, suddenly it all gathered, and you got this huge rush of water coming down the catchment and flooding lots of houses down at the end. Because, of course, people like to live beside water. It's very nice to live beside water, very nice to look at, not so nice when it comes up to say hi. So fluvial flooding in Dublin is primarily around, well, you would say the Dodder, the Liffey and the Tolka, which are the 3 rivers, but then of course there's the Poddle, and you wouldn't believe how many rivers there are in Dublin. In fact, most people have forgotten about how many rivers there are in Dublin, because when we expanded the city, what did? We put them underground. When we put them underground, we forgot about them. And every so often they came up to say hi. Sorry, we're still here. So there's rivers, particularly up in North Dublin, the Wad, would you believe is one, up around Parnell Park. And there's various small rivers in South Dublin. There's one flows down around Foster's Avenue. And by and large, people forget about them. And they're little streams, or they're mostly underground, and then suddenly they come up and remind us that they're all there. Because, of course, topography doesn't change. The land is basically still the same. It's shaped the same. We don't kind of, in large scale, change the shapes. And the driving force, which is the water, is still going to come every so often in fairly large amounts, because that's the nature of weather, which we'll come to in a minute. That's fluvial flooding. From a forecaster's point of view, and from trying to anticipate what the flooding levels might be, how far up will it rise, when will it rise, how long will it stay high, fluvial is relatively easy, and the longer and slower the river, the easier it is, because the more time you've got to make measurements and to estimate and so on. So you can have gauges upstream, and you can measure how high it is, and then there'll be a flood wave, if you like, coming down the river, and you can estimate how much volume is there and all that sort of stuff. So fluvial flooding, even though it's a challenge, is, from a scientific and engineering point of view, not the worst challenge. And then because it's mostly in a river basin, a river bed, you can build high walls up either side of the river, or do something like that, do hard defences to try and guard against it. We kind of move offshore now and move to coastal flooding. And we saw lots of that this winter on the west and south coast. So here you're dealing with lots of different things. Coastal flooding is quite complex. First of all, you've got the tide, and that's driven, of course, by the moon, so that's a gravitational thing, so it's up and down and up and down. But it's not just up and down regularly. There's spring tides and neap tides, so sometimes the high tide is higher than at other times. These are the spring tides. And some years, the springs are higher than they were the previous year. So this year we had very high spring tides. We might see them again for 10 years or 15 years or whatever. This has all got to do with gravity, which is something I'm not an expert on, but people who do the astronomy and all that can. Tide tables are very predictable. You can calculate the height of the tide, at least the base height of the tide, as far ahead in advance as you want to once you know the orbit of the moon and all this sort of stuff. But then, of course, on top of that, you've got to put the weathery bits. And the weathery bits are pressure, wind, rainfall, and also things like what we call sea surge and waves. So you've got lots of things which are added to or subtractive of the height of the tide, which depend to some extent on the weather. And not just the weather where you are, but maybe the weather 500 or 1,000 kilometres out to the west. So we'll take the easy ones first, is pressure. I mean, we know about the mercury barometer. So we have an evacuated tube, and we put the bottom of it into mercury, and lo and behold, the mercury goes up to about 76 centimetres up the tube, because that's the weight of mercury that is supported by the weight of the air, which we call the pressure of the atmosphere. So if you think of a column of air from here up to the top of the atmosphere, it weighs that much, the same amount as 76 centimetres of mercury. So as pressure rises and falls, of course it bears down on the sea, or for low pressure, if you like, it allows it to rise more. And it's a fairly significant amount. It's a centimetre of rise for every millibar or hectopascal of pressure. A centimetre doesn't sound like a lot, but for a really low pressure area passing overhead, maybe down to 950 or 960 millibars, hectopascals, centre of a low pressure, you're talking of half a metre, which is a lot of height, a lot of water to be sucked up, if you like, just purely on the pressure effect alone. Then, of course, you've got wind, onshore winds and so on, and that's going to push up the water onto the coast. Sea surge is a bit more complex. Sea surge is where you've got a big weather system way offshore, typically. Could be 500,000 kilometres offshore. And the effect of the wind on the water is it's all kind of piling it up. It's like you're in your bath, and I wouldn't advise this now, as physicist knowledge you are, and take a hairdryer or something and you blow the surface of the bath. Especially if you're in the bath, I wouldn't advise it. If you're not in the bath, it might be easier. And you'll see that the water will be pushed up against one side of the bath. So the pressure of the air from the hairdryer, if you like, the wind will actually force the water, push it up. So the one side of the bath, the water level will be slightly higher than the other. So the wind does that in a big way, if you like, out in the oceans. And you get this sea surge, which can be a metre, 1.2 metres, 1.3 metres, whatever. It can be in that sort of range. So again, a significant amount, significant height extra to add to your high tides. Then, of course, you've got waves, and waves are the local effect, if you like, of the waves breaking on the shore. And the big thing about waves is they can cause huge damage because there's lots of energy there. You've got this great mass of water, momentum. M is big, and U is big, the velocity. V squared is obviously big too. So you can chew up all sorts of stuff that's on the coast. And normally the coast is kind of protected because the water is at a level where the stuff that's getting hit is the stuff that's always got hit, and anything that was to be chewed up has been chewed up long ago. When you rise the level of the water by 1.5 meters or something, and now it's further inland, it's in over your promenade and where your various seats and playgrounds and whatever are, and they're getting battered or onto your piers or whatever. So that's the coastal flooding. I mean, what happened in the Hinch and those places over the winter was an example of that. What happened in Cork was a little bit different. That was effectively tidal flooding, added to by low pressure, added to by wind. And I haven't even mentioned rain yet, because, of course, if you've got a river running down and it's swollen because of rain, well, there's another couple of tens of centimetres of height, if you like, that you can add to your water level. So coastal flooding is complex. There's lots of different things that come together, or in most cases, of course, some of them are additive and some of them are subtractive. and they net out, and it's not so bad. Some cases, when they all add up in the same direction, then we're in trouble. The one thing about coastal flooding is because it's a large-scale effect, if you know, the weather systems that give rise to it are big systems. They're inherently fairly predictable. Tides are obviously fairly predictable. So, in theory at least, we should be able to predict coastal flooding fairly well. Maybe not exactly how high it gets in every bay, because that will depend to some extent on the local topography. But in general, we'll have some idea. Now, the third kind of flooding.
Somebody's on the cable. Stop.
Local problem. The third kind of problem of flooding is also a local problem, a very local problem. It's what we call pluvial flooding. And this is the sort of flooding we get when we get intense downpours of rain, which can actually be very small in terms of their geographical extent. They can maybe be only from a cloud that's only maybe 5 kilometres by 5 kilometres in extent, if you like, if you're looking at it from aloft. So they're small, but really intense. The real problem with pluvial flooding is that you have no idea where it's going to happen. I mean, at least river flooding is going to happen beside the rivers. Coastal flooding, by and large, will happen on the coast. Pluvial flooding can happen just about anywhere. If you happen to be under one of these clouds and it's depositing 20 millimetres of water every 10 minutes on top of you, the drains are not going to be able to handle that. Not in this country anyway. Not in most countries, to be fair. And what happens is the whole drainage system just can't handle it, and the stuff builds up, and it'll take hours for it to kind of dissipate through the normal drainage system. This is the sort of flooding we had here in Dublin, in Blanchardstown, Finglas, down that side of the city. I think it's about 6 years ago. We had it in Cork about 2 or 3 years ago in Douglas. And it's the one which really, meteorologically, is by far the biggest challenge, because the nature of the weather systems, the convective showers, as we call them, the big shower clouds that give us this flooding, by nature, they're what we call stochastic. That means there's a high degree of uncertainty associated with them. So we cannot predict their development in any kind of deterministic or reasonable way. So we're right back to our wave functions and our uncertainties here. We can look at the weather chart and say, effectively, these are driven by temperature differences between surface and aloft. So these clouds happen because air at the surface rises, and there's a big temperature difference between down below and up above, and that drives, that's the engine, that's the energy source that drives the formation of the cloud, and ultimately the release of the rain, and yes, the lightning and the thunder too, because that all comes as part of the package. So we can look at the charts and say, this is a day when we're going to get lots of those big heavy showers. All we don't know, really, by and large, is where. We give a guess of when, because the diurnal cycle of heating and cooling and that, but even that can be only a guess. Because when we get little pockets of air that begin to rise, so we get bubbles, if you like, of warm air forming on the surface. And you might get a bubble of warm air forming over, say, a supermarket car park. Big area of black. We all know black is a good absorber of infrared radiation, so the temperature of that surface is, significant. Might be temperature of a surface like that could be 30, 35 degrees easily on a sunny day, whereas the grass next door is only 15 degrees. So suddenly this bubble of warm air begins to rise, and that's the kind of starting point for what turns into a massive big cloud which drenches some town 50 miles away to the east. And it's that sort of small-scale beginnings, these little small-scale beginnings to these shower clouds that really make them impossible with our knowledge. I mean, technically speaking, if you knew where every molecule of air was around the country and what conditions it was experiencing, it's a bit like your problem with bouncing the ball against the hat. You could solve it, but it would take you an infinite amount of computer time to do so, probably, given the number of molecules of air there are. So this is the uncertainty bit that's built into it. And to give you an idea, when we had that big flooding in Blanchardstown 5 or 6 years ago, and the M50 was flooded and so on, went back and looked at that, and the cloud that caused that was kind of a part of a stream of clouds which formed over the Slieve Bloom Mountains. And 4 hours before that flooding, they didn't exist. They just didn't exist. So you're trying to plot that sort of movement and estimate that development and say, will it dump here, or will it maybe wait another 10 kilometres and dump over in Clontarf? You don't know until it starts to dump. So that's the sort of flooding which, in some ways, is really, really difficult to guard against. And this is also the sort of flooding that gave the Dundrum situation. And interesting enough, Dublin City Council did a very interesting thing after that. They said, right, well, we don't know where these big dumps of rain might happen. They could happen anywhere over the city. So we cannot assume any place is safe. So what do we do? They surveyed every basement in the city to know how many basements were inhabited, because there was one poor lady lost her life in a basement that got flooded in that event. I found there's 22,000 basements in Dublin inhabited. 22,000 potential death traps if one of these showers happens to dump in and around that area. And that's a society, if you like, how we have to respond to these things, because we cannot control these things. Our knowledge of them, we have to accept, is limited in terms of precision of where and when they'll happen. So we have to really think through the impacts and say, well, if it's going to happen, let's plan for it. So a lot of the thinking about flooding now at the sort of engineering level and strategic level, it's not about really building flood barriers in the old sense of building big walls and so on. It's summed up by the phrase, room for the river. This is in the case of river flooding. I mean, rivers always had natural floodplains over which they would spread. And of course, if we're going to build on those floodplains, they'll spread out there anyway. So a lot of the thinking now is we create that room, we allow for the fact. So we have a nice little linear park along by the river, which they had in Cork, in the Mardyke, until they built an art gallery on it and stored the paintings in the basement. Really very bright. But there we are. I mean, this is an obvious thing when you think of it, but you know, so many people had gone through those plans, and architects, engineers, whatever, people have kind of looked at that and said, we may have a difficulty here restoring things underground in an area that is a floodplain, and there's a river over there. So this is where, I suppose, coming back to this basic knowledge of science, you know, a higher level, a broad appreciation across society is in some ways just as important as getting those outer boundaries pushed out, though obviously they are hugely important as well, increasing our knowledge, increasing our understanding. Where meteorology is concerned, it's quite interesting to talk about the probability and so on, because that's where meteorology is going now. Meteorology is really moving away from what we call deterministic forecasts, where we say, well, tomorrow the rain will come at 3 o'clock, it'll clear by 7, the temperatures will reach 16 degrees, and then the next day will be a showery day, and the next day will be this, and the next day will be that. So now we're really much more moving towards probability. So we give uncertainties. The further ahead you look, you know, the more useful in a sense that approach can be, because whereas with modern weather forecasting now is reasonably good for kind of 3, 4, 5, 6 days ahead. As you look beyond that, sometimes you can fairly confidently see a pattern, and sometimes you say, we don't actually have a clue, because depending on what this system over here does, whether it goes that way or that way, the weather in 5 or 6 days could be, there's a whole range of scenarios, and really we can't say anyone is more likely than another. That's useful information, even though it's in a sense non-information. It's useful information to people who have to make decisions, because it gives them a basis. But they've got to be pretty sophisticated to take that and kind of apply it to real-life decisions, because we're used to trying to get kind of definite information to make real-life decisions. Incorporating probabilistic or uncertainty information into real-life decisions is a big challenge. I mean, even for us as physicists, as scientists, that's actually quite a challenge. For your average Sean or Sarah citizen out in the street there, it's a lot more than that, you know. So this is where the education bit, I think, is really, really important. Right, I've probably filled my time, I'm not sure, but happy to take any questions or talk about weather generally. Except I have no idea what the summer's going to be like.
Gerald, thank you so much. I learned an awful lot there, so great. I hope you have loads of questions every year.
Happening, or is it just
yeah, it's a huge area of research at the moment. So we know there's global warming, that's happening, but the signs of global warming are happening. It's all a question of scale. You look for different things at different scales. So global warming is a long-term trend. So you look for it in things which have a long-term signal, like glaciers, like Arctic sea ice, where the response of what you're looking at is in a sense determined over long time periods. It's not like last week's weather, where you begin to get the noise, if you like. Now, one of the reasonable postulates of global warming is that we're having more heat in the atmosphere, therefore we're having more moisture in the atmosphere, because the relationship between what the atmosphere can carry in moisture and temperature is very striking. A degree rise in temperature means a big increase in the amount of moisture the atmosphere can carry in vapor form. So it's basic sort of physical chemistry stuff. So if we heat the atmosphere, we will have more moisture in it. If we have more moisture in it, we have more potential for energy, because moisture is the carrier of energy in the atmosphere. I mean, the atmosphere works by basically the sun beats down on the equator, it heats the sea, the water is evaporated up, the evaporated water, if you like, is carried in the air north and south to the poles, where it recondenses, releasing all that latent heat. Latent heat is really the driver. If we had no latent heat, we wouldn't have weather. And so that basically release of latent heat is a driver of the energy, fundamental energy source for weather systems. So if we have more moisture, we're going to have more energy, and we can predict in a general hand-waving kind of a way that we will have more extreme weather. Now, start doing the statistics on it, and it gets a bit more difficult. Because, of course, there's a natural amount of extreme weather anyway. I mean, a natural variability in weather. So trying to discern, the natural variability from the underlying increase in extremities is a really tricky statistical business. It's probably, and this is why, when journalists ring us up with this being flood or whatever, the first thing they'll say, is this global warming, Well, you cannot say it's global warming. You cannot say that any one event is caused by global warming, because you're looking at a statistical problem here. You could look at, the way they're looking at it is, well, the events, you take something like Hurricane Sandy or whatever, take an amalgam of events over a year. You'd say, in an unchanged atmosphere, we would expect this to happen once every 100 years. In the atmosphere as it is today, we think they're happening once every 30 years. So you're looking at trying to compare statistical averages. And unfortunately, that's understandable to us, but the person who has to make a solid decision, particularly a politician, spending money, that's not good enough usually. And unfortunately, I think it'll have to wait until those statistics go like it's actually lads once every 5 years now, instead of once every 100, before we actually begin to make decisions. I really feel that because climate change is such, and I'm not talking just about our political system, but globally in the political system, climate change is such a long-term problem, and our political systems are so focused on relatively short-term issues, as in years to decades, no longer than decades, by and large. There's a mismatch there, there's a scale mismatch, and I'm not confident that the political system will actually cope with climate change until it's almost too late. Maybe it will be too late.
Over here.
Do government authorities or like on top to consult matters when the time
they do in a way. I mean, a lot of the basic weather information is taken by the engineering agencies, particularly the Office of Public Works, and translated into local thresholds, I suppose, particularly for flooding and stuff like that. So it's through that process the information gets fed into the system. The Office of Public Works are currently doing a major flood risk assessment management program on a lot of the rivers around Ireland. Again, this is kind of in response to the flooding in 2009. But it was underway anyway, and that's giving us a better understanding. Well, if the water rises, it's fairly basic stuff at one level, though it's not easy to do. If the water rises half a metre, well, here's the area that will get flooded. If it rises 80 centimetres, it'll be this area. If it rises a metre, it'll be that area.
Well, what you were saying about heat generated over Carpac,
they really haven't. The climate change projections haven't really made their way through to the planning system yet, because I suppose they're not. They're definite in a scientific sense, but I suppose they're not accepted or mature enough to be accepted in the engineering sense.
Yes, I have a question for you, if you don't mind. Sorry, apologies. Just wake you all up there. This probabilistic statistic associated with your weather predictions, when do you think that might start filtering in and my grandmother will be worried about her math skills, thinking, can she wear a dress that day or not?
Yeah, it's already there in some of the public media. We don't use it yet, but if you look at Swiss television, you'll see a kind of a 5 columns for, today, tomorrow, whatever, say it's, what day is today, Monday, so Tuesday, Wednesday, Thursday, Friday, Saturday, and they'll give the forecast. And at the top, they'll give a score out of 10. The fiability, as they call it, so it might be 8 out of 10 for the first couple of days, dropping off to 4 out of 10 for the last day or two. So it's already there in some presentations of the weather in the media, and probably in the internet too, or internet-based. We haven't really developed to the point of being able to do that yet, because it's a public education thing apart from anything else. People need to understand what information you're giving them here.
Yeah.
I heard it said, I got it straight, the satellite technology for meteorology. What's the next big development in meteorology?
Satellite information was crucial to meteorology in that it gave us images of parts of the world that we knew nothing about. We knew nothing really about what happened over the oceans. Nobody had ever seen the spiral weather system until the satellites came along. Nobody had that image. They had reckoned that what they looked like, but nobody had seen it to kind of verify it. But oddly enough, it's really computing power which has driven, and the development of the models, numerical weather prediction models, which has driven meteorology even more so. Though at the moment, we'd say the two go hand in hand, because the information that drives the numerical prediction models nowadays comes about 97% from satellites. Only 3% of it comes from ground-based observation systems, which is amazing. So, somebody mentioned, I think, that they'd seen our new high-resolution model. I think Shane mentioned it on television. So we're using now, where you do the sums, if you like, numerical weather prediction, you effectively cover the area you're interested in with the grid, and you do the sums on the grid points for computing purposes. And the global models are global. The grid goes right around the globe. So the global model we use, or we have access to European Centre for Mid-Range Weather Forecasting, which is a European conglomerate, has a 16-kilometre grid. So 16 kilometres is the shortest distance it can resolve. And anything that happens in weather terms at shorter spatial scales, we have to put in a kind of a fudge factor to allow for them. We can't represent them explicitly. So our high-resolution model for Ireland currently is working at 2.5 kilometres. So that allows us to get down to much more detail, to model the coastline and the topography and so on in a much more detailed way. And importantly, it allows us to explicitly model these shower clouds, which cannot be modelled on the coarser grids because they're just too small for the grid. But at 2.5K, that's what you can do. And now you begin to get a much more physically sound weather model, because you can better represent the physics in a real way rather than putting in fudge factors here and there to try and relate to things which your computational methods can't really manage. We hope to get that grid down to about 1 kilometre. It's all about computer power. And it's not just a question of a 2.5%, because every time you go to a shorter time scale, you've got to shorten your time steps and whatever, and you kind of increase the computer power by a factor of 10 or something. It's not my exact area, but I'm aware of the problems. But as you get to finer and finer scale, you will get more and more precise descriptions of what the weather will do, which is not to say that it will always be more accurate, but they'll be more precise. They'll give you better information, but not always the best information. Just coming to that, this European Centre story, physicist, meteorologist told me, we were chatting over a beer at a conference, as one does. And this is the European Centre for Mid-Range Weather Forecasting. It's a conglomerate of about 29 different European countries that kind of pool their resources. I mean, we put in, Ireland puts in about $500,000 a year into it. The Germans probably put in about 30 million a year into it or whatever. It all goes on GDP. So they're really leading the charge towards this ensemble or probabilistic forecast. They call it ensemble because what they actually do is they run the model, in their case, 52 times. And they get 52 different possible evolutions of the weather. And they do stats on that then. So like it's 52 different forecasts. Take your pick. So he was saying, there's 3 great institutions in Europe. There's CERN, where we really want to look at the smallest things that are happening. What's happening at that subatomic level? Then there's European Space Agency, looking out to the stars and looking at the big questions out there. And then there's the European Centre for Medium Range Weather Forecasting. Really, this is all about probability, deterministic. Do we live in a probabilistic universe, or otherwise, does God exist?